Greetings, everyone. So let's go and look a little bit at the homeworks from trees. There are more things that we can do with trees, and I also will do a little bit of a review for a quiz on trees. But let's go to the two special problems that I assigned. And this one, let me read the question because it's a little bit involved, the description of it, but it's not so hard. A chain letter starts with the person sending a letter out to 10 others. We have now discussed what chain letters are. So each person is asked to send a letter out to 10 others. So they're still the same, but now comes something else. And each letter contains a list of the previous 6 people in the chain. So in other words, at some point here, so this is a big tree, right? So there's a lot of things happening here. So let's look at one particular of these nodes. And then it has, this guy will send out 10 letters. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay. So you see it's very awkward already to draw this, and that is just one instance of it, right? So this is 10 people that he sends out. And what is on the list is the names of the letter that he gets has a list of 6 people before him. Well, to be more precise, you remember there's only one unique path, right? So he had somebody who sent a letter to him. So there was one guy in front, above him. Then there was another guy that sent a letter to that person. Then there was another guy sending a letter to that person. There and there, so 1, 2, 3, 4, 5, 6. So there are many more edges here. So there's a lot. Oh, sorry, no, I don't want to use this. So there are many more stuff here. But as far as the letter receiver is concerned, he gets it from one guy who has gotten it from the guy before, one of the guy before, guy before. So these are the 6 people that are before him. Right? 1, 2, 3, 4, 5, 6. So these names, their names are on the list. Now, what does he do? He has two things. He has to pay $1 to this guy, or $10. How much is it? So, unless there are fewer than 6 people in the list, but let's not talk about that. Each person sends $1. Yes, $1 to the person on top of the list. Okay, and what he then does is, then he scratches out. So he now in his letter. This is the list that he gets. These 6 people. Yeah, perhaps. Sorry, let me do this a little bit differently. So these are the 6 people that appear in his list. Now he's going to send 10 letters to his followers or whatever you want, and what is the change that he makes to this list? What he does is he deletes the top person and puts himself in the bottom. So in other words, let me put this in yellow. This is the list of people that these guys are getting. Each of the children of the previous one gets the name of these 6 people. So in other words, what does each of these guys have to do? Who are they paying? So who is this guy paying? He's going to pay this guy at $1, and this is going to go $1, and this is $1, right? So you see, it's not just that that if you're in the exchange you just only get $1. There are many people that will contribute to you. And that is really a pyramid scheme, a pyramid scheme, right? You are saying, okay, if you keep sending this, you will get a lot of money because people will keep paying you. And the system seems to be fair in the sense that it's not true that you get paid forever. Otherwise, the person that starts accumulates enormous amount of wealth, right? No, after... That's not true. So how long do you get when... Okay, so now let's analyze this. So this is a big, huge tree, right? There is even much more stuff happening all over the place, right? I'm just taking out a really little tiny excerpt of what happens, right? Okay, so first of all, what tree do we do here? Well, it is a full ternary tree. Are we convinced of that? We already discussed that chain letters by their design, are always full emery trees. And M is the number of letters that you're supposed to send. Because you either comply and you send the 10, or you say, "Forget, I'm not doing this. It's ridiculous." Okay, so it's a full ternary tree. So the question is now, so suppose this goes on forever. Of course it cannot, right? At some point there are going to be so many leaves that there are no people to send to anymore. So you're not supposed to be sending to anybody else. It's not even entirely clear how you keep track of that, but just say, okay. So let's go on saying, unless there are fewer that say, no, I'm not going to say this. If no person breaks the chain, and no one receives more than one letter, how many money will a person in the chain ultimately receive? So what is the promise? Because they want to sell to you to do this, right? And of course, I mean, this is kind of harmless in the sense you're investing one single dollar because you're giving it to one person, right? That's the only thing you have to do. So your cost is $1. Plus stamps perhaps for the other ones, but even that nowadays we don't have to do letters by mail anymore. We can do letters by email, and that doesn't cost us anything except for the $1 that you have to pay, and then you're free of that, right? So it's amazing. Only $1 you have to pay, and that's it. Now, how much are you going to make? Okay, so let's think. When are you here? So I'm always considering myself from this guy's point of view, all right? When are you gonna collect money? Now, let's see. When this guy collected money after a chain of 6. So if this is the child, the grandchild, the great-grandchild, the great-great-grandchild, the great-great-great-great, okay. After 6 generations, that person is going to give him $1. None of these are giving him $1. Why not? Because let's look at this guy. Why is this guy not giving $1? Because he's not on top of list of this guy. How the list of this guy look like? Well, the 6th on top, and he's only paying the 6 generations back. So this guy will not pay money to this guy. Will only pay money to this guy. Okay, so that's because everybody is only paying $1. And he has to go just 6 steps back. And I might say, that sounds excessive to go 6 steps back, but there's a reason for that, because that's how you make a lot of money. Okay, so you only get paid, so this guy will only get paid if one of these guys keeps sending, well, I'm assuming they all do, so everybody is really sold on this thing, right? This is like, oh wow, it cost me $1 and see how much I can make. So what is happening? This guy is gonna send 10 to 10 different people. So let's follow one of these guys. Let's follow this guy. He says, I'm gonna send it to 10 different people. Well, let's pick just one of the 10 people he picks. There are many more, right? But just let's look at one of them. Okay, so this guy is complying again, says, okay, I'm sending a lot of people, and let's follow one of these guys. Okay, this is another one. I'm gonna need space here, so let me myself. So how far away? Let's do this one more time. So a lot of so here are 10 different things, and let's look at one of them. Is this one? Let's see. 1, 2. What do we do? 1, 2, 3, 4, 5, 6. So, okay. 1, 2, 3, 4, 5. No, okay. So 1, 2, 3, 4, 5, 6. So I'm just gonna keep doing this again. 5, and we look at one of them. He sends out 10, and we look at one of them. So I'm only looking at one of them. So there are many, many more instances, right? So again, ... But my point is this. Let's look at who everybody in this chain is paying. Who is this guy paying? The one on top of his list. Remember, the orange is now the list that this yellow guy gets. So he pays this guy, right? So who is he gonna pay? Well, this guy will disappear. This guy will send a new letter with this guy removed and himself in last place. Notice that this guy is now in second last place. So he has moved up one step. Okay? So if you want it, it's going to get a little bit overwhelming with all the colors. So perhaps I'll circle it. So for this guy, the list consists of these guys. Okay? That is the list that the next guy gets. So, okay. What do I have for this one? How does his list look like? Okay, let's okay, yeah, that's okay. We don't need this. There's too much colors otherwise. So okay, let's look at. I'll keep a color for this guy. So we did this one. So now let's look at this guy. Okay, who is on his list? Well, it's 6 predecessors. 1, 2, 3, 4, 5, 6. So it's the 6 predecessors he's going to pay. So he's going to pay this guy at $1. Okay, all right. So let's move on. I'll keep coloring them. So who is this guy going to pay? Well, how does his list look like? What are the names on his list? Is 6 predecessors. 1, 2, 3, 4, 5, 6. So this is the guy he's going to pay out. All right, this is this guy. What is this guy going to pay out? Okay, I don't know why I'm taking different colors. It's not really necessary, right? So 1, 2, 3, 4, 5. No, sorry, this guy. Right? Sorry, we're talking about this guy now. 1, 2, 3, 4, 5, 6. He's paying this guy out. So finally, this one. Okay, so this one is now also done. So finally, it's the last one that let's focus now on the last one. Sorry, yeah, I don't know why I kept coloring this thing. So this one, it says, what are on my list? This guy. So I have to pay this guy $1. So the orange guy is getting paid if this letter has been sent 6 times down. Okay? So in other words, as far as the orange is concerned, it says, look, I don't care who I paid the $1 to. I paid the $1, that's gone. Now I want to know how much I get. So what is relevant for me? Well, relevant for me is the tree that consists of me being the root, and that goes down, how many levels? 6 levels down. So this is 6 levels. We didn't discuss this much, but if you have a tree and you can prune the tree, and you get always a tree. If you throw out everything on top and a couple of things in the bottom, you still have a tree, right? So because everything that keeps connected is still a tree, because it doesn't have a path, circuit. So the guy says, okay, forget about everybody else. I'm just going to look at the people that I sent a letter to and the ones that they sent a letter to. So, in other words, he's concerned, is interested in the yellow people, in the green people, in the blue people, in the red people, in the, well, I don't know why I didn't have this color, in the pink, in the gray people. And what I'm really interested in is into, what should I do here? Purple, in the purple people, because the purple people are going to pay me. So what is the tree that I now look? If you forget everything else, what tree is this? Well, it is still a full ternary tree. Okay, it's a full ternary tree, and the question is, how many leaves does it have? Because so if you chop it off, the leaves are exactly the purple guys. So you want to know what is L here. Okay, so how many leaves does it have? That is the question. Now, this is a full ternary tree, but it is much more. It's a complete ternary tree. That means there are no other leaves than on the 6th level. Okay, so let's calculate how many vertices on the 1st level are there. How many yellow vertices are there? So here's the number of vertices of a particular level. Okay, there are 10 yellow vertices. How many green vertices are there? So this is this level, right? So he's himself. So he's looking at his own interest for his own interest, his own income. He doesn't get income from the 10 yellows, but they're gonna generate for him an income, right? They're gonna make sure that he gets the income. So there are 10 yellow. How many green are there? So the next generation. But every yellow will have 10 children, so 100. So how many blue are there? 1,000. So how many red are there? 10,000. Because each of them has, so how do you calculate the number of gray people? Well, every of the 10,000 red people has 10 descendants. So by the product probability, there are going to be 100,000 gray people. And each of them is sending 10 letters, so that multiplies it again with 10, so I get 1 million. So there are going to be 1 million purple people. Okay, so this is the formula. Remember, we had this formula that the number of leaves is at most the arity times the height. Okay, so what the height here, we want the height to be 6, right? That is why we talk about the height, 6 levels. So that means, I said 6 levels, so that means height 6. But the better word is height. So height is 6. Okay, h, we call that h. Okay. So the height is 6, the multiplicity, m, the arity is 10, m is 10 in this case. So we know that this number is 10 to the power 6, that is a billion. That's the most number of leaves that you can get. But I give you an example, if every single internal vertex, now every vertex is internal in this thing because it keeps going, right? We assuming this never ends. So everybody is internal here. That means if it's what we call a complete n-ary tree, then you get the maximum number. Okay, so the maximum number is exactly attained in this particular case, and that's why we have a million. Okay, so that's, of course, so a million leaves, and each of them is going to give you $1. So he's going to collect $1 million. So this sounds an enormous good thing, right? But what can go wrong? Well, what can go wrong is that you run out of people. And of course, 1 million people, the chances are very big that somebody's getting this letter again and says, oh, well, no, I'm not going to do this anymore. I did this once and I'm still waiting for my money, right? Because if I send this to this guy here, he has not gotten anything yet, right? It's not has been his time yet. I mean, even his father or his parent has not received money yet at that time. So he's going to say, stop, I won't do this anymore. So unless you have a system that makes sure that you don't send it to the same person, yeah, sure. But then also think, how much is it going to be if the original guy starts and you have like 12 or 13 levels? We're talking about 10 to the power, the number of levels, right? The height here, we get always these maximum leaves. And as the height goes more and more, if this continues, then the height of this thing is more and more. Of course, it doesn't, for the orange guy, it doesn't matter anymore what happens later than 6 steps. But suppose it goes on more than 6 steps, you're running out of people, right? 10 to the power 6, okay, million, 10 to the power 7, 10 million, 100 million. Now you're already the size, almost the order of magnitude of the US. Do another one, 1 billion, the size of another one, and you're outside of the number of people on Earth. So that's, of course, why this doesn't work. Well, sorry, I shouldn't say it works. People have used this and made money of it, but it only works for a very limited time. As soon as too many people are involved, if 1 million people are involved, that is already not going to work. So it is a nice premise, but it only works if there are infinitely many people, and you can keep sending money to each other. That's a money scheme. This is the basis of these so-called pyramid schemes. That if you look it up, Google it and see what it is. It's a type of fraud. It's a type of it's not something that is, you might think, you can recognize as easily that this is a pyramid scheme. Well, people that have done investments, bankers, and hedge funds have used this principle and have been accused of pyramid schemes, and it's illegal. But so it's a very much more common than you think it is. It's of course more well hidden, but it exists. And it is because the promise is enormous, right? You pay $1 and you wait a little bit. Let's say everybody does this within the day. After 6 days, you get $1 million. Why would you not do this, right? Okay. And true, you never lose. Well, the worst you use is $1, of course. Okay, so here. But then, after all, this is also what happens if you buy a lotto. The worst I can do is lose $1. Okay, you do that and you don't win. So what you say, the next day you say, okay, I'll buy a lotto ticket. The worst is $1. But it still adds up, right? Okay. So number 33. The number of, I'm going to do only 33b. The number of isomers for C12, C5H12. Remember, the general setup is to be an isomer, you have to have N. If you have N carbon, then you have to have 2N plus 2 hydrogen. And it asks you how many are there. Now, that's not an easy question. So I'm just going to, there are 3, and I'm going to give to all 3. So if I would pose the question, I would say, okay, find 3 non-isomorphic isomers of C5H12. I don't know whether that has a name in chemistry. I'm not a chemist, so I'll leave that up to the people. Okay, so first of all is the one that you can always do this. You put them all on a row, the carbon, and then you fill it up with hydrogen as much as you want, as much as you need, right? I'm not drawing the lines with the hydrogen anymore, so that, of course, I'll do it here very quickly, but so that's what I mean here, okay? But okay, let me do it. It looks a little bit better. Now, you have to be careful. You have to make sure that you have 12. 5 top, 5 bottom, and 2 on the sides. So this is a valid isomer. Remember the the conditions. The degree of H has to be 1, and the degree of C has to be 4. Every C has to have degree 4, every H has degree 1. Now, you might be tempted to say, okay, I arranged the things a little bit, sorry, I'll arrange it a little bit, let's arrange it this way, and then fill up with H. But be very careful, like, okay, so how would that be? So this, this. It sounds like, it looks like you have a different, I discovered a new molecule. You didn't, because it's the same as the previous molecule. It's just that you kind of have bent this thing here, right? You made instead of going straight, you went here down here with this C, and you moved the H's around a little bit. You moved them a little bit around, but it's the same. What should I say? They are isomorphic as graphs. And remember, I told you it's not easy to see that things are isomorphic, but in this case, it's not so hard to show that just mapping this C to this C to this C, and the previous C's to what they are, you get the same. So this is not a new one. Okay, so I'm going to erase it. Okay, so here's another one. Now, this is not easy, and it took me a while to find them too. Here. Okay, you can put the C's into a star, like in this setup. So let's see. Then we have 3 H's here. We need 3 H's here, 3 here, and 3 here. So again, this is how it really is, right? And again, look, always check that my conditions are verified. Now, why is this definitely not the same as the previous one? Because this C has only C neighbors, whereas most here, what do we have? These 2 C's have only 1 C carbon neighbor, and these 3 inside ones have 2 carbon neighbors. Okay, but here's a C that has no hydrogen neighbors, but 4 carbon neighbors. Okay, so this is clearly different than that one. Now, let me do another one here. So this is this one. Okay, and I connect them this way, and I say, okay, let's fill up with H's. So we need 2 more here. How many do we need? 1 more here, right? Let's write the connections. Here we need 3 to make the 4. You remember, we always have to have the right amount of bonds, right? Bonds. So we have 1 here, 1 here. Also, we have 1 here, and perhaps 1 here. Don't connect these 2, right? Because then you would make a circuit. So this satisfies all the requirements, except how many H do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is not of this nature, and therefore this is not a valid isomer. I don't know the chemistry behind it, but for some reason this is impossible as a molecule. This would be C5H10, not C5H12. Okay, so this is not an isomer of that carbon hydroxide. So it's not just arranging things. It would be different, of course, because yeah, it's not even yeah. So the last one is sorry. Let me see. How did I do it again? Here. It's how did I do it? 3. Ah, yeah. So this way. C C C C. Wait. No. Sorry. That's not right. This is the way. Bonding like this, and so just what you can do is you can look at the subtree consisting of the carbons. Just look at the carbons. Ignore all the hydrogens, all the H's. Then this is just a line, right? This is a different graph, right? And this is yet a different graph. Why are the different graphs? Well, here every part that goes from a pendant, remember pendant is one of degree 1, is of length 2. But here this is a pendant, but there's a part of length 3 to them. And here there's only 2 of degree 1, and there's a part of length 5. Here there are 4 of degree 1, and here are 3 of degree 1. So it's also different. If you just count the number of degrees, it's different. Now, it doesn't mean that this gives me an isomer, because I have to still attach my H's to it. Remember, here we had this pattern, right? If you just look at the C's, it was a smart pattern that I had. But the problem is, if I fill it up with H's to make the degrees fit, the bonds fit, then I don't have enough H's. So that's the only thing I have to now check. If I fill this up to make sure that all the carbons have degree 4, this is exactly what I need to do, right? I hope you agree that this makes everything have degree 4. All the carbons have degree 4. Now, how many H's do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So these are the 3 isomers, and what I say is much harder to prove that these are the only 3. Okay? Somehow the textbook finds that an easy question, but I don't see at all how that is easy. The whole point is, though, that they are 3 all different. So I repeat, why are they different? One way is to just look at look at the subtree or the subgraph of just the C's, ignoring the H, right? Then this has 2 vertices of degree 1. This graph has 4 vertices of degree 1, and this graph has 3 vertices of degree 1. So you see that even that already makes them all 3 different. And if that's different, therefore the whole thing cannot be the same, right? Because that's just by adding H's. That doesn't change the way that the C's behave relative to each other. Okay, that's for the homework.